All right, let's jump in. Class recording is started. Jordan wants you to ding the bell. So, Jordan wants you to ring the bell. So, make sure you do so. Okay. All right. Yesterday. Yeah, it's a little rowdy. All right. Yesterday we finished up our drawing that shows all of the orbitals that surround the nucleus of the atom. We talked about quantum numbers that we use to represent or to distinguish those orbitals from all the other orbitals that exist around the nucleus. So then yesterday, right at the end of class, we got into this idea of the fact that yes, all of those orbitals exist around the nucleus, but that doesn't mean there will necessarily be electrons in all of them. For two reasons. One, most atoms, or a lot of atoms, don't have enough electrons to fill up all of those orbitals. And two, because they all correspond to different amounts of energy, some orbitals are more likely to have electrons in them than other orbitals. So we started off yesterday talking about what we call the Aufbau principle. The Aufbau principle says that orbitals get filled from the ones that have the lowest energy to the ones that have the highest energy. And because the idea of quantization was introduced by Bohr, quantization meaning, right, that the location of an electron relates to the amount of energy that it has, different orbitals have different amounts of energy. The ones closer to the nucleus have lower energy, so those are the ones that get filled first, and we go outward from there. We talked about this chart that you guys have on the first page of your outline, actually these two charts. They both basically tell you the same thing, but I like the one on the left a little bit better than the one on the right. I think it's a little bit easier to read. And so, like it says along the left-hand side, or if we want to think about that as the y-axis of this chart, right, it says increasing energy of electrons and orbitals, and there's an arrow pointing upward. And that means we're going to read this chart from bottom to top. That orbitals closer to the bottom of the chart are going to have lower energy than orbitals that are higher above them in the chart. Okay? Good with that so far. So an actual orbital diagram shows us the distribution of electrons within the orbitals. We use a circle or a box or a line to represent the orbital itself, and then we'll use arrows to represent those electrons, showing where those electrons are within those orbitals. Okay? Good? Kind of good.
If there's more than like one electron, is it
Yeah, hold on. That's where we're going today. Okay? All right, so yesterday we started off and we made our first orbital diagram, and that was for hydrogen, right? So we start off and we go here, right? And we did this right at the end of class yesterday, so here's hydrogen. So the first thing that we have to do when we're drawing an orbital diagram, because the orbital diagram shows us the distribution of electrons, we have to know how many electrons we're dealing with. How are we going to determine how many electrons an atom has? What tells us the number of electrons that an atom has? Its atomic number, right? So we go to the periodic table and we find that hydrogen has an atomic number of 1, so we have to place 1 electron. Okay? So the first thing we're going to do is we're going to go to this chart, right? And we said we're going to read this chart from the bottom up. So the first orbital that we come across closest to the bottom of this chart is 1s. So yesterday I drew a line that represents the orbital itself, and then underneath that line I wrote 1s because that represents which orbital it is, and because there's only 1 electron there, right, we'll use a single arrow to represent that first electron. Okay? Yes? The half arrow kind of saves time. So when we start getting into orbit or electrons that have lots of, when we get into atoms that have lots of electrons, the half arrow might save a little bit of time, but it really doesn't mean anything different than a two-sided arrow. So again, it depends on most of the time it depends on what book you're looking at. So some books will use double-sided arrows. Some books will use single-sided arrows. It really just depends on the book you're reading. I suppose that's true. All right, good. Okay, so the next one on your list, is helium. Okay. First thing we have to do is we have to go to determine the number of electrons that we have to place here. So we find helium on the periodic table. Its atomic number is 2, so we have 2 electrons. Okay? All right. Again, we start down at the bottom of the chart. The first orbital that shows up, the one that has the lowest energy of all the orbitals, is the 1s orbital. So we're going to draw a line. We're going to label it 1s. Okay? We've already said that we know that an electron will go into that 1s orbital. But is that orbital full? No. Yesterday we learned that each orbital can hold a maximum of how many electrons? 2, right? We call that idea the Pauli exclusion principle. Okay? Each orbital can only contain 2 electrons. However, we have to distinguish between those 2 electrons. And we say that those electrons have what we call opposite spin. Notice, spin is in quotation marks. It doesn't necessarily mean that the electrons are spinning in opposite direction. It's a way for us to tell one electron from the other electron. So, in order to show that in our orbital diagram, to show one electron being different from the other electron, we draw one arrow up and one arrow down. Okay? So, our orbital diagram for helium looks like this. Okay? All right. Good? Good for starters? Okay. Next element on your outline is lithium. Okay? First step in the process, we have to determine how many electrons. 3, right? Lithium has an atomic number of 3. That means it has 3 protons, but it also means it has 3 electrons. We go back to our chart. 1s is the lowest energy orbital. We draw a line, or maybe if we want to do it a little differently this time, because sometimes you'll see it. Sometimes you'll just see a box, okay? Doesn't matter. Means the same thing. We can label that box 1s, okay? Hold on. All right. So, here's our 1s orbital. We know that this 1s orbital can hold how many electrons? 2, right? And how do we distinguish the 2 electrons from each other? One arrow up, one arrow down. Okay? So Jack, we can just go like that if we want to. Okay? All right. Here's where lithium gets a little bit different. Okay? Is that orbital full? Yes, that orbital is full. Each orbital can only hold a maximum of 2 electrons. Okay? But how many electrons does lithium have? 3. That means we need another orbital. So we go back to our chart, and we said we're going to read this chart from where to where? Bottom up. 1s is the orbital that's closest to the bottom. You move up the chart, the next closest one to the bottom is a 2s orbital. Okay? So, we're going to draw another box, right? What are we going to label it, Kendall?
2.
We're going to label this one as 2s. Okay? All right. How many electrons will this orbital have in it? 1 electron. Okay? All right. Good there? Okay. The next one that's on your sheet is boron. Didn't we just do lithium? Ah, So next on your sheet is boron. Okay? Good, good. Hold on. We'll get there, Claire, promise. All right, let's do boron first. Because Claire, it's much easier to identify the patterns when we have less electrons to worry about, but we'll see that as we add more and more electrons, the pattern holds. It's just a matter of having more arrows, right? There's a pattern of how these go and how they get filled up and stuff like that, okay? All right, so boron. First thing we have to do is identify a number of electrons. How many electrons are we talking about now? We're talking about 4, maybe? 5 electrons. Okay, so orbitals get filled from lowest energy up. First electron, or first orbital is 1s. So I'm just going to go back to drawing lines. We'll label that one 1s. How many electrons can this orbital hold? 2 electrons. But we got to distinguish them from another. 1 up, 1 down. Okay? That orbital is full, but we've only placed 2 of the 5 electrons. So we go back to our chart, right? Next orbital we come across is 2s. Okay? Draw another line. Kendall, I'm going to label this line what? 2s. How many electrons can that orbital hold? 2. So there and there. We've now placed how many electrons? 4 electrons. But boron has how many? 5. So now we got to go back to our chart. Even though it's in a different column, which set of orbitals are next closest to the bottom? 2p. First, the fact that they are p orbitals should tell you something about them. What are p orbitals? Hourglass shapes, right? But just like we did on our drawing, how many hourglass shapes show up at the same time? There are 3. There's one on the x-axis, there's one on the y-axis, there's one on the z-axis. If you look on your drawing, how many little lines are there next to 2p? There are 3. But what are you noticing about how high each of those 3 lines are compared to each other? They're the same height from the bottom of the chart to the top of the chart. What is that telling you about the energy of all 3 of these orbitals? They're all exactly the same. Okay? It doesn't matter that one's on the x-axis, one's on the y-axis, and one's on the z-axis. They all have the same energy. So, what does that mean? That means when we come across a sublevel that has multiple orbitals, like p, or later on when we get to d, we have to draw all 3 of them. Because they are all exactly the same energy. And then we can label them all as 2p. So usually what I do, just to kind of save some time, is I'll just label them like that. Okay? When we get to something that has multiple orbitals, like we have there, we have to label them, or we have to list them all. Okay? Now, and this we'll change this in just a second. Okay? Where does my 1 electron go? Ethan said the first one. What do we know about all the energy of all 3 of those orbitals? Exactly the same. Does it matter where we put that single electron? Not really. It really doesn't. For the most part, when you're looking in a book or whatever, you will see just that single electron drawn in the one to the far left. But quite honestly, it doesn't matter where we put that single electron. What else wouldn't matter at this point in time? There's one other thing that really doesn't matter when we're just talking about this one single electron. Is that orbital diagram wrong for boron? Nope. Right? We have 1 electron. All 3 of those orbitals are exactly the same energy, so it doesn't matter where that single electron goes. And is the direction that the arrow points important? Not if what? Not if there's only one electron. It's important if there's two electrons. What has to be true about the two arrows in the same orbital? They have to be opposite, but if there's only one electron there, it really doesn't matter. Okay? Now, like I said, for the most part, you're going to see that single electron drawn upwards in the orbital to the farthest left, but quite honestly, any one of those single electron would be fine. Okay? Good there. Okay, here's where things get a little different. I believe the next one on your list is carbon, is that right? Yes. Okay. You go to the periodic table, you find carbon's atomic number. What is carbon's atomic number? 6. So we have to place 6 electrons. Okay? Lowest energy orbital is always going to be what? 1s. So here, just to break things up a little bit, I'll draw circles here. Okay? So here's 1s to represent my 1s orbital. Okay? How many electrons can this orbital hold? 2 electrons. One arrow up, one arrow down. No, that's another thing too, Ethan. Yeah, doesn't really matter if you draw the down arrow first and the up arrow second. As long as they're different from each other, that'd be fine. Okay. All right. Next lowest energy orbital is 2s. I'm going to draw a second circle. I'm going to label it 2s. How many electrons can that one hold? 2. Okay. Changed it up. Really doesn't matter as long as they're different from each other. Okay. Next lowest orbitals that we come across are what? 2p. But like we said the last time, how many 2p orbitals are there? There are 3 orbitals. So we're going to draw all 3 of them. 1, 2, 3. We're going to label all of them as 2p. Okay. Now, here it does make a difference. Okay. We said that there are 2 sort of overarching principles that determines where these orbitals go. What are the 2 things that electrons are trying to accomplish as far as arranging themselves around the nucleus of the atom? Closer to the nucleus, okay, but farther away from each other, right? All 3 of these orbitals are the same basically distance from the nucleus. They all have the same energy. Okay? So, if electron number 5 goes here, where is electron number 6 going to go? Is it going to be the same circle? No. These are all the same distance from the nucleus, so they all have the same amount of energy. But if the 6th electron goes here, what is it getting close to? That other electron. Does it want to be close to that other electron? No. So, if we have multiple options, electrons are going to try and spread out as much as they can. So electron number 6 could go here. You want to open it? I'll do it. Hold on. Jet, you have an appointment at 12 times a day.
Called it.
All right, so electron number 6 could go here. Where else could electron number 6 go? Could go in that last one. Where couldn't it go? In the first one. Okay? All right, good for carbon for starters. Okay, now I'm going to actually add one on here. Okay? So there's a little space down at the bottom of your page there. Let's add another one that isn't on your sheet. And let's add oxygen. Oh, sorry, we gotta fill in some, no, underneath neon, okay? All right, oxygen. Go to the periodic table, oxygen has 8 electrons, okay? I realize we skipped something, or I'll come back to it in just a second, okay? All right, oxygen, 8 electrons. We always start off in which orbital? 1s. How many electrons can that orbital hold? 2. 1, 2. All right, next orbital we come across on our chart, 2s. How many electrons can this orbital hold? 2. All right, next group of orbitals that we come across, 2p. As we've discussed, there are 3 orbitals. Here's 2p. Okay. All right, here's where we have to make a value judgment, or we have to understand what we're doing here. Okay. How many electrons do we have left to place? We have 4 electrons left to place. So, I'm going to put electron number 5 here. Okay? Where's electron number 6 going to go? Next to it. And then where's electron number 7 going to go? Next to that one. Okay. We've now spread out those 3 electrons as evenly as we can. Okay? But we still have 1 electron left. Where is it going to go? Glad you said this. Okay? So Jordan said it's going to go 3s. Do we understand why Jordan said it is going to go 3s? Okay? It's the next one up, right? There's 3s. However, how many electrons can each of those orbitals hold? 2. Are these orbitals full yet? No. We have spread them out as evenly as possible, but those orbitals are still not full. Okay? So, we're not going to jump up to 3s until all of the 2p's are full. Even though that means we have to pair up 1 electron in a 2p orbital, this is still less energy than jumping up to the 3s orbital. Okay, so when we have multiple options, okay, like we do with the 2p orbitals, electrons are going to spread themselves out as evenly as they can before they start doubling up. So every orbital in this section, every orbital in 2p, is going to get at least 1 electron before any of them get 2 electrons. Okay, but before we jump up on the chart, we still have to fill all of these electrons. Okay? We call that idea, and I don't think you guys have anything to actually fill in here, right? We call that idea Hund's rule. Okay? Hund's rule says, I don't think you guys have to fill in anything in. I think it's written for you, right? Okay? On your outline underneath carbon. Okay? Electrons will not pair up within orbitals until each orbital within a sublevel contains at least 1 electron. We try to distribute them as evenly as possible. Basically, if we have multiple orbitals that have the same energy, like the 2p orbitals, each of those orbitals gets 1 before any of them get 2. Okay? Good there? All right? So, on your outline, let's jump straight to sodium. Which I think is at the top of the next page, yes? All right. You go to the periodic table, you find sodium. How many electrons do we have to worry about? 11. Okay. Actually, yeah, let's do this one. Okay. All right. First orbital we come across is what? 1s. How many electrons can that orbital hold? 2. 1 up, 1 down. Next, that one's full. Next orbital we come across is 2s. That orbital could also hold 2 electrons. It's now full. Now we go to 2p, right? Like we've discussed. There are 3 2p orbitals. We'll label each of them as 2p. Okay. Now, On a test, I wouldn't be able to tell if you did this or not, but from a sequential order, right, we've already placed 4 electrons. How many do we have left to place? 7 left, okay? Now in a test, I wouldn't be able to tell if you did this, but just for the sake if you're watching the recording or something like that, right? 5 goes here, 6 goes here, 7 goes here, 8 goes back to the first one, then 9, then 10. Okay? Say again? Well, like I said, if you see that real quick, like, oh, I'm going to fill all these up, and you just go through and do it, I wouldn't be able to tell whether you did that on a test or not, right? But if we're talking about Hund's rule and the idea that things spread out evenly as they can before any of them double up, that's how we would fill, okay? Now, how many electrons have we placed? 10. But, right, we have 1 left to go. What are you seeing about all of these 2p orbitals? They are all filled. Now we go back to the chart. Now, Jordan, what's the next orbital that we come across? 3s is the one that's next closest to the bottom, right? So now we're going to add another orbital, right? We're going to label it 3s. How many electrons are going to go in that orbital? Okay, Ethan, go ahead. Yes, there is. Okay. So, not just the 3s, but let's back up for a second, okay? So, go ahead, Yasmin.
Will that chart right there that you're using the left hand?
Yep, that's going to be on your test, yes. Yeah, you will have this chart on your test, okay? In chemistry, like when you go to chemistry next year, there is a way for you to use the periodic table to basically, the periodic table gives you this chart, but I'm not going to make you memorize that right now. I'm going to give you this chart on the test, okay? Don't worry about that right now, okay?
How are we going to ever need to memorize this
The periodic table?
in this school?
I don't know if you need to memorize, I don't know. So, probably not the whole thing, so. Sorry, didn't want to cough in the microphone. So. All right, so Ethan, let's talk about shorthanding this, okay? We're going to back it up just a second. Let's do neon, which is at the bottom of the previous page, okay? So, neon has how many electrons? 10. Okay? So we're going to start here, 1s. That's full. 2s is next. Now that's full. We've placed 4 of the 6 electrons so far. 2p. Okay. Again, I don't necessarily expect you to do this on the test, but if we're going sequentially, right? Electron number 5 would go here, electron number 6 would go here, electron number 7 would go here, 8, 9, 10. Okay? Good? Okay, Ethan, let's talk about why we can do this, all right? So, here is my orbital diagram for neon. Here is my orbital diagram for sodium. What are you noticing about the first 5 orbitals? They look exactly the same, right? So, here's what we can do. All of this and all of this are exactly the same. So what we can do is, we can start off our orbital diagram for sodium by putting neon in square brackets just like this. Okay? This is now going to represent how many electrons? This is going to represent the first 10 electrons. But we still have how many left over for sodium? 1. So then we can go here, right? And now we've shorthanded this. But here's the deal, okay? Here's the deal. you can only shorthand using elements in the far right-hand column. Okay? Column 18 on your periodic table. What do we notice about neon here? They're all full. What the whole one level is totally full. The whole second level, all the S's and all the P's, totally full. We can use that as a shorthand or shortcut. You cannot just pick the previous element to whatever element you want to on the periodic table and use that. We can only shortcut using those elements in the far right-hand column, column 18. Okay? Good?
Yes.
All right. We will pick it up from here tomorrow. We'll do a couple more practices with the orbital diagrams, and then we will talk about being even shorter than that. Okay?
Yeah.
Your quiz will become active today. It only goes up to orbital diagrams. There's nothing that we're going to do tomorrow that is on the quiz. So if you want to take a look at it, you can, or you can save it until tomorrow night when we have another day of practice in class. Okay? Quiz